So just as a reminder of what we've done before, if we have, this kind of applies to an operating systems example, but if we had a process arrives, goes to the CPU, so it's coming off of the ready queue, so you could think of this as the ready queue, and it's going into the CPU, and it processes for a while, and with a certain percentage, after it's done processing, it goes back into the ready queue again. Sometimes, while it's processing, it has a page fault, and it'll go out to the disk drive. And then after it's done with the disk drive, it goes back to the ready queue. So processes are coming into our queuing system from the outside world. They'll run for a while and maybe they'll time out and go back to the ready queue. They'll run for a while and then maybe go out to the disk drive and then go back to the ready queue, and then eventually they leave our system. And they're done for the day. So the operating system, this is the disk. If there's one disk drive on your system, on your computer system, the operating system can monitor as the day's going on what the percentage of time this stuff happens. So if there's a percentage of time, let's say it notices that 20% of the time, any process that gets on the CPU, 20% of the time, it hits a page fault. And 30% of the time, now let me make it 70% of the time, it times out and goes back to the ready queue, and 10% of the time, it finishes. So if we want to keep track, there's a few statistics we want to keep track of. The things we want to keep track of is how much time, what is the rate of stuff coming into the CPU? What is the speed of the CPU? With those two numbers, we can calculate what percentage of the time the CPU is in use. And then if we knew the speed of the disk drive and we knew the rate of, oh, I need to put a Q in front of this. We need a Q in front of the disk drive because the request coming into the disk drive are queuing up. And so the rate into the queue is going, we have to figure out what the rate into the queue is, and really the only thing we know is the rate into our overall system, but then based on the percentages, we should be able to figure out the rate into the disk drive. We know the speed of the disk drive, so with the speed of the disk drive and the rate into the disk drive, we can figure out how many processes are in the queue on average when we arrive. How long will they take? How long will it then for us to take, so we get the total amount of time we'll spend in this queue. And then we come back here. The other thing we have to figure out is, we want to know, from the moment we enter the system, how long would it take for us to finish? That's important to us, on average, the average turnaround time. So we have to know, for every time we enter the system, how many times will we revisit this queue? Then we want to know how much time we spend at the queue times the number of times we go to the queue. And the same thing is true for this one. And then add it all up, and that'll tell us how long we spend in this system. So just as a little refresher, if the rate coming into the system, if anyone wants to make up a rate, say lambda, the rate into the system is 2 per second. For every time a process comes in to the queue from the outside world, into the system from the outside world, how many times will it visit the CPU? Well, if it just goes in once and leaves, then it's one visit. But this looks like it goes in, and then with a certain probability, it revisits again. So the way we calculated the expected number of visits was, we said, the lambda, we'll call this the overall lambda. Lambda, again, is the Greek letter we use to mean the rate into a queue. The lambda into the system 90% of the time, 0.7 plus 0.2, 90% of the time when we go into the queue, we go back to the beginning. So the expected number of visits, equals, well, we're definitely going to visit it once, that's for sure, because the first thing we do is we come in and visit. So it's going to be 1 plus, and then 90% of the time, 20% of the time we go to the disk drive and we come back to the beginning. 70% of the time we just time out, the operating system times us out, and we go back to the ready queue. So that's a total of 90%. So 0.7 plus 0.2. 90% of the time we end up coming back to this queue. Now, if we come back to this queue, from that point on, how many times do we expect to hit the CPU? That's exactly the same as the expected number of visits. The expected number of visits is, if you come in from the outside, how many times do you expect to hit this thing? That is equal to 1 plus 90% of the time you're going to start over. So that would be expected visits again. So if we right? So, hope that makes sense to everybody. The number of visits, the expected number of visits, let's say the answer is 4. I mean, that's not going to be the answer, but let's say it's 4. Well, that would be equal to 1 plus 90% of 4, if that was the right answer. That's what this statement is saying. So now we can solve for the expected number of visits. Well, now if we subtract 0.9 from each side, we get 0.1 times the expected number of visits equals 1, which means the expected number of visits equals 1 over 0.1, which is 10. So we would expect any process coming into this system to hit the CPU on average 10 times before it leaves. Could hit 15 times, could hit 2 times, but on average it will hit 10 times. So the rate from the outside world is 2 per second, but the rate into this queue, because it's this 2 plus per second plus all these feedbacks, which will be 10 times whatever the outside rate is. So the overall rate for this system, if I'm saying 2 is the rate in from the outside world, it would be 2 times 10. So the CPU lambda is equal to 2 times 10, which is 20 per second. So the outside world is feeding in at a rate of 2 per second, but as far as these 3 arrows combined, the total rate into this queue is 20 per second. Now you have to kind of look at the picture to say, what is the rate into the disk drive? Well, 20% of everything that comes into the CPU goes to the disk drive, and 80% does not. So what would the lambda, the rate into the disk be? It would be 20% of lambda CPU. And you get this from the picture. The CPU feeds something. So if it fed more things with different percentages, you would just take this and the percentage of this, the rate into this device times the percentage that go into another device. And if that accumulated with other queues, that would be like an example we went over 2 classes back, where you have 3 different things feeding a queue. You just add them up to get the total rate into the queue. So this would be 20% of 20 per second. That would be 4 per second. So the rate into this queue, the rate into the disk drive is 4 per second. The rate into the CPU is 20 per second. The rate into the overall system is 2 per second. So now we have to figure out, when we arrive at a queuing system, so that's a queue and a thing that services customers. Put those two together, it's a queuing system. When we arrive to the CPU queue, how much time do we spend at it? And we're going to visit it on average 10 times. But we want to know each visit, how long do they take? So if they take 3 seconds to visit, 10 visits, that's 30 seconds. So how much time do we spend when we arrive there? And we have to say to ourselves, when we arrive at the queue, on average, how many customers or processes do we expect to see in front of us? If we're using the queuing discipline of first come, first serve, then everyone in front of us goes before us. If we use any different discipline, this question will become a little bit harder, but not a lot harder. But the easiest one to follow is first come, first serve. So, how many customers do we expect to see at a queue when we arrive at it? Now, what we said last time was that if the queue was an M1, this is just a reminder, the first M comes from the mathematician Markov. So it's Markovian in the rate at which it comes in, and the server is Markovian in the rate at which it goes out. So let me just explain that again. So one thing to be careful of, whenever you're doing applications of anything is where you learn a theoretical concept, and then you take the theoretical concept and apply it to something. If you apply it, it becomes an application. So if you learned in a math class that 1 plus 1 equals 2, and then you tried to apply that concept to fruit, you could say 1 apple plus 1 apple equals 2 apples. So that's an application of 1 plus 1 equals 2. You could say 1 orange plus 1 orange equals 2 oranges. That's another application of 1 plus 1 equals 2. But if you said 1 apple plus 1 orange equals 2 apples, you're not applying the concept correctly, right? Because apples and oranges are two different things. So, when we said last time that the way to calculate how many processes are in front of us, we said if the arrivals were Markovian and the services were Markovian. And what did that mean again? That meant that they have an average service time, like an average rate of 2 per second, but the average gap between the two is completely unpredictable. So from when the last event happened until the next event happened, there's no information about the past that helps you with the future. So they of course have an average. If you saw a series of events happening, and every time an event happened, you added 1 to your count, and you had your stopwatch, and you look how long it took to have 10 events occur, you could figure out an average of how much time it was between each event. They can be perfectly scheduled. That would be a DD1 queue. Deterministic distance between the two events coming, and a deterministic scheduled service time. Whether it was an MM1 queue or a DD1 queue, it would be like the apples and oranges analogy. They're two different queues. So just for example, if the arrivals were deterministic, suppose the arrivals coming into the system were 2 per second, coming into this queue, we're at a rate of 2 per second, but then we said that translates into 20 per second because they get multiplied by 10 in this system. Suppose they arrive at a rate of 20 per second into the queue, and this CPU can service mu equals 20 per second at a rate of 20 per second. Suppose we had every arrival come in exactly 1/20th of a second apart, perfectly scheduled. And this thing not only services them at a rate of 20 per second, but they all take exactly 1/20th of a second, exactly. Not that one takes a long time and one is very short, but they all take exactly 1/20th of a second. That would be a DD1 queue. What we would expect every time we arrive at that queue is nothing to be in front of us. Because the guy in front of us was done right before we arrived, and we finished right before the guy behind us arrived. There would never be anybody in front of us, because everything's perfectly scheduled. So that's one extreme, the the deterministic case, the gap between the times are exactly scheduled perfectly. The total opposite extreme, where it's totally random, is the MM1 extreme, the MM1 case. And in the real world, there are always some hybrid of the two. So if you take like a whole course in queuing, it starts off with an MM1 and a DB1, and then you start to realize that's not really true for the real world. The real world is somewhere between the two. But we're looking at only the MM1 example in this case. So the DB example, the expected number of customers in front of us will either be 0 if the utilization, the percentage of time this is in use, is 100% or less. And if, for example, we're sending in too much work for this thing to handle, it'll just go, the queue will go off to infinity over time. In the case of the MM1 queue, we could have the the CPU being in use only half the time, and yet when we arrive, there may be stuff in front of us. It could have went a long time being idle, and then a whole bunch of work came in at once, and that's why we're queuing up and stuff. So this application only makes sense for the MM1 queue. I just wanted to say that. So our result last time was, we said the expected number in front of us was equal to, it was, what was it, rho, percentage of time the device is in use divided by 1 minus rho. We did that birth death analysis only for the MM case. And then we found out the expected number would be rho of 1 minus rho. So we started putting numbers on this. If we said 20 per second, and this thing moves at a rate of 30 per second. If this thing can handle them at a rate of 30 per second, then the rho of the CPU, the expected number in the CPU, would be 20 divided by 30 over 1 minus 20 divided by 30 equals 2/3 over 1/3 equals 2. So this was only true. So this is like I'm saying with apples and oranges, don't get them confused. This formula is only true in the MM case. Actually, in the MM1 case. If we had more servers, we could talk about that at the end of class. It would change too. Okay. So when we arrive at the CPU, which we expect to hit it 10 times, we also on average expect, with the numbers I'm now putting in here, we now expect to see 2 customers in front of us when we arrive on average. Half the time, 1/3 of the time, this thing is idle, right? If the rate in is 20 per second and it operates at a speed that gets stuff out at 30 per second, 2/3 of the time it's doing something, 1/3 of the time it's sitting idle. But when we arrive, on average, we would expect to see 2 customers in front of us. 1/3 of the time we're going to see nobody in front of us. 2/3 of the time we're going to see something in front of us, and if you average it all out, it'll come to 2 customers on average. So we're going to visit this thing, and then we're going to, on average, see 2 customers in front of us. Then we go, so a total of 3 customers have to be processed for us to get out the door. And so that would be 3 customers, and this thing's working at a speed of 20 per second, so it would be, 30 per second. So it would be 3 customers. The expected time would be 2 customers in front of us plus us, 3 customers, at a rate of 30 per second. So that would be 1/10 of a second. So we arrive at the CPU 10 times. We're going to hit it 10 times before we finally get out the door. Each of those 10 visits will each take 1/10 of a visit. 1/10 of a second. So total time, total average time at the CPU would be number of visits times average time which would be, and I'm just making up these numbers, would be 10 visits, 1/10 of a second each. That includes the two processes in front of us, plus us. So that would be 10 times 1/10, which is a total of 1 second. So our process, which will hit the CPU 10 times, each visit taking 1/10 of a second, will spend a total of 1 second at the CPU. Now, we do the same analysis on the disk drive. How many times we go to the disk drive? We go to the disk drive 2 times. Because for every visit to the CPU, 20% of those go to the disk drive. So we'll go into the disk drive 2 times. And how long will we spend there? Well, the rate into the disk drive is 20% of the rate into the CPU, and the rate into the CPU is 20. So this would be 4. So the lambda, so this is, I'll just do it here. The lambda into the disk drive equals 4 per second. And let's make up a service time that's makes the math easy. We're going in 4 per second. We'll make it work at a speed of 8 per second. Let's make it math easy. So I'll say the mu for the disk drive is 8 per second. I had to pick a number bigger than 4, otherwise this queue would go off to infinity until it would get clocked out. Okay, so if the arrivals are also Markovian, meaning the gaps between those 4 per second are totally random size gaps, which is probably not true in the real world because the CPU will, there are going to be certain jobs that just hit their time quantum and start over, and there'll be a number, the rate at which they go into the disk drive would be probably in multiples of those time quantum blocks and then a random time. It's probably like 8 fixed times and then a random time, instead of just a totally random time. But we'll model it like it's an MM1Q. So the rate into the system would be what? The rate into the system was 4 per second. We decided to make the mu 8 per second. So since it's an MM1Q, the expected number in front of us, the expected number in the queue at a random point in time would be 4 over, it would be 4 over 8 divided by 1 minus 4 over 8, which is 1. A half divided by a half is 1. Okay. So we expect to see one customer in front of us. Now the truth is, depending on what disk algorithm we use for fetching the files, that's going to affect this number. And we could alter it if we don't like this number, and we think a different searching algorithm will make things better. The operating system would do that. But we expect to see one customer in front of us, so the amount of time we'll take for the whole queue would be the one customer in front of us plus us. So that's 2. So the expected time equals 1 plus 1, and times, we could do 8 per second. It moves at a speed of 8 per second. So 2 divided by 8 would be 1/4 of a second. So that's a pretty fast disk drive relative to the CPU. So we're going to visit this disk drive 2 times before we get out the door. Each time will be, each visit will be 1/4 of a second each, so 2 times 1/4 equals a half a second. So we will spend a total of 1 second at the CPU, 10 visits, 1/10 of a second each, and a total of a half of a second at the disk drive, 2 visits, each visit 1/4 each, and that includes all the stuff in front of us. So the total time for us to get in the door and out running would be 1.5 seconds. So you add up the total time you spend at each device, and that would be the total time in the whole system. Okay. So suppose the question was asked in a way where we didn't have these numbers, we're just looking at hit and miss ratios. So suppose we had this drive like this. We have a disk drive, I'm sorry, a CPU and a disk drive. And we have a certain hit and miss ratio. I'm not even drawing the cue. So we have we could call this a hit ratio. And then if we go out to the disk drive, we have to come back and go to the CPU. So let's say the time it takes each visit to the CPU is little t, and the time it takes to go to the disk drive is big T. So like in the last example we had, well, that's okay, that's the total amount of time a visit to the CPU takes. And then this is, the disk drive is going to be something much bigger. So, what is the utilization of the CPU? What percentage of the time is the CPU in use? That would be the lambda into the CPU, lambda into the CPU times little t, the amount of time spent in the CPU. Right? Time spent at something is the reciprocal of the service time. So if we can do 30 per second, then time spent there is 1/30. Okay, the time spent in the disk drive would be equal to let me write this out a little bit more clear. When we say lambda CPU divided by mu CPU equals little t times lambda CPU. The disk drive would be the same thing. Lambda disk, mu disk equals big T lambda CPU, lambda disk. Okay. Right, so really this is a similar question, just I'm using theoretical numbers, not real numbers. I'm using little t and big T. Now we would like, out of these two devices, we want our hit ratio, because we're the operating system. So we can adjust the hit ratio by giving more page frames to the process. So if we're unhappy with a certain hit ratio, we as the operating system can do something about it. If we want the CPU to be the bottleneck. What does the bottleneck mean? That means out of all the devices, that's the one that has the highest percentage of time in use. Why is it called the bottleneck? Because if we start sending in more work, out of all the devices that we are routing work around to, all the different sub-queues, as soon as one of them hits 100% use, you can't add any more work. If you add more work, the queues are just going to go off to infinity. So, and then your system would be totally saturated. So, once the utilization of any device hits 100%, this system we have to stop letting jobs in until we get stuff to finish. We always would like the CPU to be the bottleneck device. We want that one to be the thing that's in the most use, because all the work that hits the system requires that every instruction that needs to be executed has to eventually be executed. So we don't want to spend so much time with the disk drive that the CPU is sitting idle when we can have the CPU work hard. So if we want the CPU to be the bottleneck, what do we have to set little t and big T to? We would want T times lambda CPU, whatever the lambda of the CPU is, we want that to be greater than or equal to big T, lambda CPU. If that was the case, then the utilization of, because this is basically, like I say, this T is really the reciprocal of mu. So we want the miss ratio to have this property to it. So then we can say little t divided by big T, and then the miss ratios cancel. It has to be less than or equal to the miss ratio. So this is just a formula saying that whatever the speed of the CPU is, that's the operating system will know what the speed of the CPU is. And then we're monitoring the speed it takes every time we go out to a disk drive request. We keep an average of how long it takes for the request to come in. If the files are link allocated or sequential, that'll determine what big T ends up becoming. But we have to allow enough frames so that this stays true for every process. We want to give enough processes for this to be true. So whatever the time is at the CPU divided by the time it takes at the disk drive, we would like the miss ratio, how often we take this path, to never go higher than that percentage. So for example, if the CPU works 10 times faster than the disk drive, we don't want the miss ratio to go higher than 1/10. If it goes higher than 1/10, if it's like 1/9, there'll be more traffic queuing up at the disk drive than at the CPU. So then if this process went on further, we'd have to shut down the system because too much work is going into the CPU. I'm sorry, into the disk drive. So does that part make sense? So really, this is basically what we're doing is the question we had before about hidden miss ratios going off to one. Right now we just have a disk drive, but we could then turn this into a cache and then a certain percentage that missed the cache go to main memory and so on. We could just make the question get bigger if we wanted to. And we want to manage our resources so that the CPU is always the highest utilized one. That's the one that will get eaten up in resources first. Once our system eventually shuts down, we can't let any more work in. We hope that the CPU is at 100%. If the CPU is not at 100% and then we have to shut down our system, then we're not getting work done optimally. Okay. So then, another example would be, if we could put a couple of these concepts together, would be if we had a queue like this. The queue goes into a CPU, and some of the time, work gets routed to one disk drive or one device. And these don't even have to be disk drives right now. I should actually change this example to be something more interesting. But for now, we'll say that's disk drive 1. Some work gets routed into a queue for disk drive 2. This is now files of your file system on your operating system is being scattered across multiple disks. But when you go from the CPU, it hits a page fault and the page is on one disk drive. We go to that disk drive. When we're done, we always go back to the CPU. So there's work coming in from the outside world, and then a certain percentage of the work just hits its time quantum and the operating system makes it go back into here. And then a certain percentage of the time after it executes its last instruction, it leaves our system. Okay? So suppose we have the lambda from the outside world is lambda equals 1 per second. And let's say once again, this is an MM1 queue. If it's deterministic or some hybrid of Markovian and deterministic, then counting results don't work. Okay. And if the CPU has a mu of 20 per second, we have to ask ourselves, how often do we visit the CPU? Well, if I say 20% of the time we go off to this drive, 10% of the time we go off to this drive, 70, I'll make the math easier, similar to the math we had in the previous example. 70% of the time we go back to the CPU, and 10% of the time we leave the system. So all of the exiting arrows from any device have to add up to 100%, otherwise we're losing words. But 70% of the time we go back to the ready queue, 10% of the time we're done, 20% of the time we go to disk drive 1, disk 1 and disk 2. And anytime we go to a disk drive, we always, once we get the page we're looking for, we leave. I'm sorry, we don't leave, we come back to the ready queue. Now the question is, how much time does it take us to go in the door and out the door? Another interesting question is, which of these three devices is the bottleneck? And if the CPU is not the bottleneck, we need to, as the operating system, make changes so it becomes the bottleneck. So, what's that?
That's more than 100%.
What's what?
Now, that CPU is 110%. 70 plus 40.
70 plus 40?
0.7 plus 0.1 plus 0.1 plus 0.2 is 1.1. Your numbers.
Oh, wait, 7, 9, 10, 11. Oh, right, okay. Hold on. What, oh, actually, let me make this 0.6. That was good. Yeah, our numbers would have come out really screwed up. Well, not really screwed up, but. Okay, so wait, this is 20, 10, 10. Okay. So, I want to make it like the last one. So our rating to the system was 1 per second, last time it was 2. 90% of the time we come back, right? If you add up all the arrows that bring us back, it's 90% of the time. That's the same as before. That means for every time we come in, there's going to be 10 visits to the CPU. All right, so we don't have to read through that math. So lambda of the outside world is 1 per second. Lambda to the CPU is 10 per second. Lambda to disk 1 is 20% of 10 per second, that's 2 per second. Lambda of disk 2 is equal to 10% of 10, which is 1 per second. Okay, what else do we need? We need to know, when we arrive at anything, how much stuff's in front of us. So, we need to know how
You also need a view from the 2 disk drives.
Right, so we need views for the disk drive. So let's make up some easy ones. 20% going in. We got to give it a number faster than, I'm sorry, 2 per second is the rate into here, so the thing better be fast enough to get out at least 2 per second, otherwise it's going to get clogged. So, well, so we can already calculate the mu, not the mu, the row of the CPU. That is 10 over 20. CPU is in use with this rate coming in 50% of the time, right? So if we said the radio over here is, what did we say this was, 2 per second? Let's make the mu will be 3 per second. Okay? So, the percentage of the time this disk drive is in use, this 1, would be 2/3, 67% of the time. And the rate into this queue is 1 per second, so let's make the mu Maybe this one uses linked files and this one uses sequential files, and that's why it's slow. But for whatever reason, it's a slower disk drive. The percentage of time disk drive 1 is in use, even though it's a slower disk drive, less work is coming into it, so altogether it's 1 divided by 2, which is 50% of the time. So this is 50%, this is 66%, and this is 50%, which makes this guy the bottleneck. So if we start sending in more work, we're going to eventually get to the point where this thing hits 100%, and then we say no more work. And that's not good, because then we'll be at the point where we can't add any more work, and the CPU is at 100%. Okay, what else do we want to figure out? How much time does it take from when we enter the system till we leave? So, 10 visits here, we have to know how many are in front of us. This is the apples and oranges thing. If it's Markovian, then the number in front of us would be, the number in front of us of the CPU would be 10, no, same as before, 10 over 20 divided by 1 minus 10 over 20, which would be 1. Number in front of us at this 1 would be 2/3. Let's find the same example as before. We should come up with more interesting numbers. 1 minus 2/3 equals 2. And the number in front of us at this drive 2, the rate in is 1, the rate out is 2. So the number in front of us at this 2 is 1/2 divided by 1 minus 1/2. Again, this formula is only true for MM1 cubes. And that would equal to 1. So now, how much time does it take per visit to the CPU? Well, there's one guy in front of us, and there's also us. So time per visit. Time per visit at the CPU is one guy on average is in front of us, then there's us. So that's 2 time, and then it's a rate of 20 per second. So 1 plus 1 divided by 20 equals 1/10 of a second per visit. And this is like last example, times 10 visits. Okay. The next one, 2 guys in front of us plus us, divided by the rate 3 per second. So that would be, each visit takes 1 second. Each visit to disk drive 1 takes a total of 1 second. There's 2 people in front of us, then us. That's 3 people. And it works at a speed of 3 per second, so we'll take 1 second per visit. And the last one, we expect to see 1 in front of us plus us. That would be 1 plus 1 over 2 per second, and that would also be 1 second. So if we wanted to add it all up, what do we got? 10 visits to the CPU, so total time is 10 visits to the CPU, each taking 1/10 of a second, plus 2 visits to this 1, each taking 1 second each, plus 1 visit on average to this 2, each visit taking 1 second each. This all adds up to 4 seconds. So we have a throughput of 4 seconds. Obviously, if we started increasing the flow from the outside, it'll make these queues get bigger and will take more time. But as long as this is the current rate from the outside world, that's our total time in the system. Turns out the bottleneck device is unfortunately not the CPU. We always want to manage the operating system so that the potential bottleneck device is the CPU. So the operating system will always be calculating. There's a performance monitoring part of all the major operating systems that's always monitoring what percentage of time these devices are in use. And if the system is not saturated, the CPU hopefully is the one with the highest percentage of use. And if it's not, we have to figure out a way to make this go down. there's 66% that have to go down. So what techniques do we use? We could
Change the way of searching the disk.
Yeah, change the searching algorithm to something better, possibly move some files from this disk onto this disk, but we'd be trying to look for something. The performance monitoring would be trying to look for something to fix that. It's not a problem right now because there's not enough work going into the system, but if we started increasing work, we'd want to kick off something. Something that makes the device that's the bottleneck become lower, making the CPU become the top